Across the universe, stars end their lives in different ways. Some collapse quietly. Others release brief, intense flashes of radiation detectable across billions of light years. These events are called gamma-ray bursts. They are among the most energetic phenomena known in astrophysics. They are not expected to affect Earth, but if it did, a gamma-ray burst, or GRB, is a short-lived pulse of extremely high-energy electromagnetic radiation. Gamma rays sit at the highest energy end of the light spectrum. They carry far more energy per photon than visible light or X-rays. GRBS are typically divided into two categories: long-duration bursts, lasting more than about 2 seconds, usually associated with the collapse of very massive stars into black holes. Short-duration bursts, less than 2 seconds, often linked to mergers of neutron stars. These bursts release most of their energy in narrow jets. If Earth is not aligned with the jet, we would not experience the direct radiation beam. GRBS are observed in distant galaxies on a regular basis by space telescopes such as NASA's Fermi Gamma Ray Space Telescope and Swift Observatory. Most occur billions of light years away. The key variable is distance. The intensity of radiation falls with the square of distance. A burst in another galaxy is detectable but harmless. A burst within our own galaxy, aligned with Earth, would be different. GRBS are rare in the Milky Way. Estimates suggest that a galaxy like ours produces a long-duration GRB roughly once every few 100,000 to several million years. However, not all of those would be pointed toward Earth. The probability of a GRB occurring close enough and aligned precisely with Earth to cause significant biological impact is considered low on human timescales. Some researchers have proposed that past mass extinctions, such as the late Ordovician extinction around 440 million years ago, might have involved atmospheric effects consistent with intense radiation exposure. This remains a hypothesis rather than confirmed evidence. In short, GRBS are real, measurable, and physically understood phenomena. A damaging event affecting Earth is possible in principle, but statistically rare. For this scenario, assume a massive star within roughly 6,000 light-years of Earth undergoes core collapse. It produces a long-duration gamma-ray burst. One of its relativistic jets is oriented toward Earth. The burst lasts approximately 10 seconds. This distance range is often cited in atmospheric modeling studies as potentially significant for ozone depletion effects. The radiation would travel at the speed of light. There would be no warning from the gamma rays themselves. Optical signals from the star would arrive simultaneously. The interaction with Earth would begin immediately upon arrival. First minutes. The gamma-ray burst reaches Earth. There is no visible beam striking the ground, no shockwave, no explosion at the surface. Instead, the radiation is absorbed high in the atmosphere, mainly in the stratosphere, between roughly 10 and 50 kilometers above Earth. The key process is ionization. Ionization means high-energy radiation breaks apart stable molecules. Nitrogen, N2, and oxygen, O2, molecules are split into reactive fragments. For people on the ground, nothing is felt physically at that moment. The radiation does not directly burn skin or heat the surface. However, instruments would immediately register changes. Satellites would detect a sharp spike in gamma radiation. Atmospheric sensors would measure increased ionization in the upper atmosphere. Some radio communications could briefly fluctuate because ionization affects how radio waves propagate. The burst itself lasts seconds. After that, the radiation source is gone. but the atmospheric chemistry it triggered continues. First hours. In the hours that follow, the altered atmospheric chemistry begins producing nitrogen oxides, NO and NO2. These compounds react with ozone. Ozone is a molecule made of 3 oxygen atoms. It forms a thin layer in the stratosphere that absorbs most harmful ultraviolet B, UVB, radiation from the sun. As nitrogen oxides accumulate, ozone molecules begin breaking down faster than they can reform. From the ground, there would still be no dramatic visual change. However, satellites would begin measuring declining ozone concentrations. Atmospheric scientists would observe unusual chemical patterns. Sunrises and sunsets might appear slightly more reddish or muted in some regions due to nitrogen dioxide absorbing portions of visible light. At this stage, the change is chemical. Surface life has not yet experienced the full effect. First days. As ozone depletion progresses and sunlight continues reaching Earth, more ultraviolet B radiation reaches the surface. This is when the changes become noticeable. Concrete examples: sunburn would occur more quickly than expected for a given exposure time. People might notice skin reddening after shorter periods outdoors. UV index forecasts would rise significantly above typical seasonal values. Public health agencies would likely respond with guidance, limiting midday sun exposure, increasing sunscreen recommendations, encouraging protective clothing and eyewear. In agriculture, some crops, including soybeans and wheat, may show leaf damage. Farmers might observe slower growth in UV-sensitive varieties. Greenhouse cultivation would become more protective because glass blocks much of UVB radiation. In the oceans, phytoplankton in the upper layer of water would experience increased UV stress. Satellite measurements could detect reduced photosynthesis in affected regions. This would not immediately collapse fisheries, but it would stress the base of marine food webs. First weeks. Ozone depletion could reach substantial levels in affected hemispheres depending on burst strength. In cities such as Los Angeles or New York, outdoor workers would require modified schedules. Schools might reduce outdoor activities. Demand for UV-blocking materials and eyewear would increase. Healthcare systems could begin observing higher rates of acute sunburn, increased eye irritation, early signs of photokeratitis in exposed populations. These changes would not resemble a sudden disaster. They would resemble a persistent environmental shift. Ecologically, amphibian eggs, which are sensitive to UV radiation, could show higher mortality. Surface marine organisms would experience measurable stress. Crop yields in highly exposed regions might decline within a growing season. Nitrogen dioxide in the upper atmosphere also absorbs visible light, potentially causing slight surface dimming. Some regions might experience modest cooling due to reduced sunlight. These changes would be subtle, but measurable. First months to years. If ozone depletion remains significant, for example 40 to 50% in some regions, elevated UV levels could persist for years. Long-term effects could include increased skin cancer rates over time, higher incidence of cataracts, shifts toward more UV-resistant crop varieties, expanded use of indoor or protected agriculture. In marine ecosystems, reduced phytoplankton productivity could alter fish populations. Some fisheries might decline gradually as food webs adjust. Urban environments might see faster degradation of outdoor plastics and coatings, increased maintenance costs, adjustments in building design to limit UV exposure. Over years, natural photochemical reactions would gradually rebuild the ozone layer. The atmosphere would recover. But ecological and public health impacts could leave measurable traces for decades. The most significant impacts would not come from immediate radiation injury, but from atmospheric chemistry changes. Infrastructure would remain intact structurally. However, increased UV exposure would degrade materials more quickly. Agriculture would require adaptation. Food systems could experience regional stress. Technological systems such as satellites would likely remain operational, though temporary ionospheric disturbances might briefly affect communications. The severity would depend heavily on burst proximity and duration. Several uncertainties remain. What's the true frequency of GRBs in the Milky Way? What's the probability of a jet aligning precisely with Earth? What would be the exact magnitude of ozone depletion under extreme radiation inputs? How would ecosystems respond to sustained UV increases? Most conclusions are based on atmospheric chemistry simulations using known reaction rates. No modern human civilization has experienced a nearby GRB, so direct observational data do not exist. Current astronomical observations do not indicate any imminent GRB threat aligned with Earth. Gamma-ray bursts are part of the normal life cycle of massive stars, and they occur regularly across the universe, usually far from us. Earth's atmosphere provides strong protection against high-energy radiation. Its stability is part of the background conditions that make life possible. Stability is often invisible until it changes. But what if it did?